So today we're going to be talking about simulating Rapunzel's hair and basically some of the techniques that we used to actually move Rapunzel's hair in the film Tangled. So hair was actually used by every department in our building here. So today I'm just going to be talking about simulation specific for how we move the hair. We had a large simulation team full of people that were not just moving Rapunzel's hair, but also the different cloth and the other characters' hair as well that was going on. Hair is known to be one of the most complicated challenges in CG animation. In reality, the human head has over 100,000 strands of hair. Each strand is very thin and highly deformable and creates constant collisions both among the hair and between the hair and the body. Therefore, actually computing these calculations of how the hairs are interacting with each other becomes very complicated to do on the computer. Also, hair has very specific shapes and details that it's trying to hold on to, whether the hair is curly or wavy or straight, that has to be considered for the physically based simulation. So for Rapunzel, all of these challenges are basically just magnified for the length of her hair. Also in animation, we have certain artistic directions that we need to hit. Characters are often exhibiting very non-physically based motion, where a character might be running 80 miles an hour or squashing or stretching in a way that real people wouldn't. And when we're doing actual physically based simulations based on real world global parameters, it doesn't make any sense anymore if the characters that we're performing those simulations on aren't also restricted to real world motions. So we have to be able to adapt what we're doing based on what the characters are doing. And overall, in animation, we want to be able to have control over the motion. So even if the hair is doing what real hair would, it's not necessarily what we want it to do for the scene. So we really want to have control over the simulation so we can artistically drive the hair at any given time. So here's an example of an early production test that we did for Rapunzel's hair. We used a lot of tests like this in order to develop the techniques that we would eventually go on to use throughout making the film. So Rapunzel's hair is not just more complicated because it's so long, but also because the hair is just an integral part to the overall story. You know, Rapunzel's one of the main characters. She's on the film throughout most of the movie, so her hair is also on the screen. And characters are constantly grabbing the hair and touching it and pulling on it and climbing it and rolling in it. And basically, you name it, it happens with the hair in this film. Rapunzel's also a very energetic character. She's constantly running and jumping and moving and doing cartwheels, and her hair really needed to keep up with her and work with her as well. So throughout making the film, since we had so many people that were working on the hair, we had what we called the hair Bible, which Glenn Keane drew for us to be basically guidelines for how Rapunzel's hair should always look throughout the film. So she always had to have this characteristic swoop. The hair should always have these different turns and twists. There should be mass and weight to the hair. There should always be an interesting path that the hair is going to have. So even if the hair was just lying on the ground and not even moving, we always want the hair to be beautiful. It should always be in a beautiful configuration. It should always look interesting. So even if it didn't seem to be an important part to the actual scene, a lot of care was put into where the hair was placed. So I'm going to talk about some of the hair development process that we did in software engineering. So to start our process, we actually start by looking at real hair. So even though Rapunzel doesn't live in the real world, we want our hair to look like it could. So we study how real hair works, how real hair interacts with each other, how hair interacts with the character's body, and the weight and motion that hair has, so in order to know what we're trying to accomplish. From there, we started to create a physically based simulation system. We wanted to have a really strong core physical simulation in order to build on for Rapunzel's hair. So we worked on how hairs are going to pile up on the ground on each other, how they're going to interact with each other, how static friction forces work. We had a lot of structural mechanics and mathematical equations that we studied, how the hair is going to coil and hold on to its shape and waves and curls, and how really the hair is going to work from a structural level, both for individual curves and for the overall mass. Once we have a strong core physical system that we're starting from, we started to run many tests with Rapunzel as a character. And we iterated very closely with the directors and the animators of the film in order to get a good understanding of how they wanted Rapunzel's hair to move. So we would basically do a lot of tests and show them the results, and they'd basically point us in one direction or another to say the hair should be softer here, it should weigh more, it should pull less, it should glide more easily. And we would get these kinds of feedback and direction in order to understand how we should be adjusting our simulation. So really throughout making this film, it was really the art direction that drives the technology development. So for an example, I'm going to show how we handled hair dragging on the ground. So since Rapunzel's hair was so long, we figured it's going to be weighing between 60 and 80 pounds, which is, you know, a lot of effort in order to move this. Rapunzel's a very petite person, so obviously carrying that kind of extra hair is going to be a lot of burden on her motion. It's going to restrict what she can actually do. In reality, for her art direction, we wanted Rapunzel to be not limited and burdened by this hair. It should just be a natural extension of her, as if it was another part of her body. So, and she's very energetic, and she loves to run and jump and you know, do all sorts of things that her hair couldn't inhibit her. So we needed a way to be able to have the hair drag behind her in an effortless way where it still looked natural. But overall, we wanted to have control over this motion so that we could dial just one value and have it pull tighter or be looser. So some of our first tests using more natural hair parameters, we found that we started to get a really large tugging effect on the hair, where there'd be a large angle between the hair and her body. So this was a lot too much pull, so we decided to do the simplest thing first, which was basically just lowering the friction on the ground. Of course, once we did that, we totally lost control of that hair, and it's just kind of started sliding down at her far too quickly, and it looked like she was walking on ice, so you could really see the trick far too easily. We also tried things like just making the hair weigh less, but then as she would move around, it looked like she was on the moon because her hair just didn't have that right weight that real hair should have. So we want to be able to control the degree of pull the hair had with her body without having the rest of the hair come flooding at her with every step that she takes. So the way that we approached this was looking at the hair from a downward view. We actually took the friction on the ground and split it into two different components. First, we have along the hair the tangential friction that controlled the overall pull. The remaining directions controlled the slide propagation. It's not how friction works in the real world, but it works for our benefit here. And so that way, with just one simple control, we can control how the hair is going to drag along the ground and how much pull and weight that's going to have. Here's an example from the film where you can see Rapunzel running and her hair following behind her. So efficiency. Another issue with simulating hair is due to the high number of hair strands. It can be very computationally expensive trying to simulate all these hairs. So what we try to do in order to make the simulations run faster so that our artists can iterate on their work more quickly is to only simulate what we absolutely need to do. So for starters, in this little example here, we see Rapunzel moving and the hair that's around her is reacting to her movements, whereas the hair that's at the back that's on the ground isn't moving at all. And so we found it would be a large waste of computational resources simulating all that hair to actually make it not move. So what we do is we split Rapunzel's hair into three main sections. First, we have the back part highlighted in blue that was frozen, where basically the positions of the hair were always frozen, they didn't move. Therefore, we didn't actually simulate them. We didn't compute any collisions with them or spend any time on them at all. The green area closer to Rapunzel's body, we fully simulated, and it would react to her motions and collide with her body. And then the purple region in the center there is where we blended between the two so that you wouldn't see a harsh line where hair was moving versus where it was not. So similarly, we have a lot of close-ups in the film. She has 70 feet of hair, and you can seldomly see all 70 feet at the same time. So when we have a situation like this, where we can only see hair up to like her waist or her knees, what we end up doing is actually detaching it or cutting it from the rest of the hair. So we're secretly cutting off whatever you can't actually see. So this way the hair is able to simulate much faster because we don't have to worry about that back portion that you can't see, and she's not encumbered and attached to that hair anymore. Now for the shot production process. So again, we had a lot of artists that were working on the hair simulation, and we always need to be able to convey where the hair is supposed to be going at any given shot. So we have what we call these drawovers, where either the directors or the animators would draw over on the screen to indicate where the hair needed to be placed for each shot. It helped convey the art direction for the scene, as well as have consistency from one scene to the next to make sure the hair was always in a proper place. So the hair was always thought out where it was going to go, so we never just had it land wherever it was going to be. Everything was always well thought out. And for these drawovers, they could also indicate on there what the kind of motion should be, what the shapes of the hair should be. And they could also do kind of a little sketch drawing to also indicate the motion of it. So it's a few just short, simple lines to indicate what the feel of that hair should be. Then the simulation artist would go and match that using the simulation, and here's what the final version of that looked like. So again, for efficiency, we didn't simulate the 100,000 strands of hair that a typical human has. Instead, we only simulate a small fraction of 173. We're able to take advantage of the fact that hairs that are near each other tend to react similarly. So we developed techniques to simulate 173 curves and have that then drive the actual rendered hairs that we see. This also helps to have much less time-consuming simulations. So our simulation artists would basically iterate in this between simulation and rendering to see their work and to refine what they were doing. And then once they have gotten approval from the directors for whatever work they were doing, then they send on that hair simulation data to the final lighting and rendering department that does the beautiful lighting and shadows. So of course simulations don't always go right the first time. There's always something that gets in the way at some point. So that same simulation, this is what it looked like the first time we ran it. So not quite correct. It's a few things that were out of place the first time we hit play. So then we make some adjustments, run it again, and eventually zero in on what we need. But the bloopers and mistakes always made us laugh, so we kept a bunch of them. Thank you for your time.